Today's lecture is on time complexity. Time complexity, why should we care? What is time complexity of a program? Why is it important? Computers today have tremendous power and speed compared to computers 20 or 30 years ago. So why is time complexity important? We'll try to see through an example. John and Mary are two students, and they have been given an assignment. And the assignment is, given a number n, they have to find out whether n is prime or not. A prime number is a number that can only be divided by two numbers, 1 and the number itself. 2 is the smallest prime number. And some other numbers are 3, 5, 7, 11, and we could go on. 1 is not a prime number because it can only be divided by only one number, and that's 1 only. So a prime number should have exactly 2 factors. Both Mary and John figure out different solutions to the problem. John says, hey, I'll try dividing all numbers starting with 2 all the way to n minus 1. And if I can find any such number that divides n, so if I find any number between any I between 2 to n minus 1 that divides n, then n is not prime. Mary, however, is intelligent enough to realize that she does not have to check all the way to n minus 1. Only she cannot find an I to the square root of n. She can be sure whether the number is prime or not. So she says, for I starting with 2 to the square root of n, if there is any such I that divides n, then n is not prime. Whether these solutions are correct, let's say that John and Mary have handled this special case for 1 separately. Whether these will work, and we will not go into the details of why they will work, let's just assume for now that they will work fine. Now, when they both run their programs for larger input sizes, John is quite sad, while Mary has a big smile on her face. Why is it so? Let's try to see. Let's say the computer who has to run this program takes 1 millisecond to run operation. We'll say 1 millisecond for one division. Let's see what happens for various inputs for n. In the worst case, John's loop will run exactly n minus 2 times. It will run n minus 2 divisions that would happen when the number is prime. However, for Mary, in the worst case, she'll perform exactly the square root of n minus 1 times the division. Let's pick various values for n and see what the time is taken by these programs. We'll start with a small number first for n, and it's equal to 11, and 11 is a prime number, so John's loop will run starting from 2 all the way to 10, and this will take exactly 11 minus 2 milliseconds, or 9 milliseconds. Mary, however, will take the square root of n. The square root of 11 is 3 point something. We're only interested in the integer values, so the loop will only run for 2 and 3. So the loop will only run 3 minus 1 times, and the time taken will only be 2 milliseconds. Let's pick a higher value, where n is equal to 101, and that is a prime as well. John will take 99 milliseconds. Mary will take The square root of 101 is 10 point something, so the Mary will take 10 minus 1, 9 milliseconds. This is less than 1 second, and the computer won't give you a hint as to the actual runtime for such a small value duration. Let's pick a higher number this time, and we'll pick a 7-digit prime this time. This says, now it says 10 to the power 6 plus 3, which is equal to 10 to the power 6 plus 3. So John will take almost 10 to the power 6 milliseconds to solve this problem. And if you convert this to seconds, we'll have 10 to the power 3 seconds, or 16.66 minutes. Wow. And now let's see how Miss Mary does here. Mary will take the square root of 10 to the power 6 plus 3 minus 1. And for larger values, we can safely ignore this minus 1 here, and almost 10 to the power 3 seconds, which is only 1 second. Now we can see a variable difference here. While John is taking 16.66 minutes for his input, Mary is able to solve the problem in only 1 second. Now let's pick a really higher value this time, an 11-digit prime number. And the number is, which is also equal to 10 to the power 10 plus 19, and this is a prime number as well. So John's loop will run exactly n minus 2 times. So John's program will take about 10 to the power 10 milliseconds, which is equal to 10 to the power 7 seconds. If you try to convert this to minutes, hours, and then days, this will be a little more than 115 days, which is quite impractical for a program to solve a problem. And now let's see how Mary's program does here. Mary will take close to the square root of 10 to the power 10 is almost equal to 10 to the power 5. Mary will take 10 to the power 5 milliseconds, which is only 100 seconds, or 1.66 minutes. Now we see why Mary is quite happy and John is sad. Mary is solving the problem in 1.66 minutes here, and John is taking an impractical time of 115 days to solve the problem. Time complexity of a program is a simple measurement of how fast the time taken by the program grows if the size of the input increases. So if the input to the program is n, we can see that in the first case, the time taken by the program is proportional to n. We often say in computational terms that this program is an order of n algorithm. This O is called big O. You can search over the internet to see what it is. We will not go into the details of mathematical notations for now. Mary's program, as you can see, the time taken is proportional to the square root of n. And we say that this is in the order of square root of n algorithm. And we write it as big O square root of n. So we realize through this example that correctness of a program is not the only thing. What's also important is how your program behaves with larger inputs, and we should always write our programs that behaves well for larger input sizes. Until next time, see you.